Welcome to motion along a straight line. So we know that velocity is the rate of change of displacement. Displacement being a vector quantity that is a measure of distance in a straight line. Time is a scalar. Acceleration is the rate of change of velocity. Velocity is a vector quantity. It's composed of the direction and the speed. If either of those things are changing, then it means that you have an acceleration. When an object is moving, we can either calculate its instantaneous velocity, which is its velocity at any one moment in time, or we can calculate its average velocity, which is the velocity taken over a longer period of time. On the roads, you will have seen speed cameras that calculate both of these. The instantaneous speed cameras are the isolated yellow boxes that flash a couple of times very, very quickly and record your speed as you drive by. The average speed check speed cameras are probably less familiar to you. And on these pictures, you can see that there is a bar that's held across the road, and we've got 3 sets of cameras focusing on the 3 different lanes of traffic. And what they do is they record your number plate and the time stamp, and then further down the road, there will be another set of these cameras, and they will calculate whether or not you have been speeding during that time interval. They calculate your average speed across that distance. So you could go past the first set of cameras above the speed limit, but then slow down below the speed limit, and that will bring your average in line. So look out for these signs next time you're on the road, and then look out for these bars. It's quite interesting. Displacement, velocity, and acceleration can all be represented on graphs. If I have a displacement time graph, then what I'm showing is the distance away in a straight line from a particular point. So this might describe a journey. For example, a journey from home to school. So you might start off slowly as you're walking to the bus stop, and then when you get on the bus, you'll travel at a much greater velocity. You arrive, you wait for your friend, and then you both walk to school together. So notice that there are different gradients at different points in the journey. On a displacement time graph, a horizontal section, like this one here, represents 0 velocity. The gradient is 0, and therefore the velocity is 0. And that all stems from the fact that velocity is the rate of change of displacement. So the rate of change of this graph is the gradient of the graph. And where the gradient is 0, that means that velocity is going to be 0. Where the gradient is highest, that's where you have the highest velocity. And where the gradient is low, you have a low velocity. You can also have velocity time graphs, where the velocity is changing. So you may, if we emulate this journey, we may start out with a low velocity as you walk to the bus stop. You then get on the bus and you have a much higher velocity. So we have a sudden jump to a high value. And then you go down to 0 while you're waiting on the bench. And then your velocity continues at that low speed again. So this graph has now been turned into a velocity time graph. But more usually, you will see graphs where velocity is changing, where you have accelerations. One of the more common graphs that you're going to come across is that of a parachutist. And this is the shape of a parachutist velocity time graph. It starts off like this, then there is a sudden drop, and then another drop. So in this portion of the graph here, we have a rapid increase from zero velocity to a higher velocity. But you'll notice that the gradient, which starts off high, gets shallower and shallower until it's eventually zero. Now, if you'll recall, acceleration is the rate of change of velocity. And what that means is that the gradient of this graph is acceleration. So we have a very steep portion of the graph here. The gradient is very high. Acceleration is very, very large. The parachutist has just jumped out of the aeroplane. They are falling toward the ground. The faster they go, the greater the effect of drag on their body. So as their velocity increases, as they travel along the graph like this, the rate at which their velocity is increasing decreases. Acceleration is highest here and is zero over here. Notice we have a flat part of the graph where acceleration is zero. That's because they've reached the terminal velocity at this point. They cannot go any faster. If you analyze the forces on their body, we have the weight of the parachutist and we have the friction force of drag. In the first part of the journey, we have the weight and we have a small amount of drag. That drag increases the faster and faster they go. So notice that down here they have a low velocity and it gets higher and higher and higher to the point whereby they are going so fast that the frictional forces on their body cancel out their weight. They've reached their maximum speed. After this point, they open their parachute and that causes drag to rapidly increase and they decelerate. We have a negative gradient in this part of the graph, a negative gradient. So that's a negative acceleration, a deceleration, and that causes their velocity to decrease from a high value to a low value. Notice that this is the terminal velocity here, a high value, and it decreases to a low value down here. They then reach a second terminal velocity with their parachute open, and then they land on the ground. So this graph here is an excellent example of non-uniform acceleration. The acceleration is constantly changing. We have a high gradient, a high acceleration over here. We have a zero acceleration over here. We have a negative acceleration here, zero again, and more negative acceleration. So this is a great example of non-uniform acceleration. An example of uniform acceleration might be a vehicle. So a vehicle might accelerate, drive at a constant speed, and then decelerate for some traffic lights. We've got a straight line graph, and that tells us that the acceleration is constant. The gradient is constant, so the acceleration is constant. Here we have another straight line section telling us that acceleration is constant. It actually has a value of zero because it's a flat graph. The velocity is the same value all along this section. And then here we have a negative but constant acceleration as the graph goes downwards. So this is an example of uniform acceleration, where the acceleration has a fixed value. The general rules of motion time graphs are that the area beneath the line is calculated by multiplying the two things on the axes. If you multiply velocity by time, it gives you displacement. So the area under any velocity time graph is going to be displacement. If you are calculating the gradient of a line, then you look at the axes and you calculate what would happen if you divided them. Velocity divided by time is acceleration. You need to know about the behavior of a bouncing ball. So I'm going to draw several graphs and sketch out the displacement, time, the velocity time, and the acceleration time graphs. Okay, so with a bouncing ball, it will go up and then it will go down again. So I want you to imagine a ball going up and down and bouncing in the same place every time it lands. But because the horizontal axis represents time, we are going to see the pattern of the bounce move across the x-axis. So a bouncing ball is going to go up, it's going to reach a maximum displacement, and then it's going to come down again. It's going to bounce, and it's going to go up and down, and it's going to produce this pattern of behavior, this type of pattern. Okay? In reality, the ball will lose energy with each bounce. Energy will be lost as sound and heat in the material of the ball, in its contact with the floor. So we would expect it to reach a lower height each time. Notice that I've drawn the whole of this graph in the positive region. And that's because I'm considering the ground as the distance from which I'm measuring the displacement. So the displacement starts off down here at 0, so the ball is on the ground. So I'm starting my experiment just after the ball has bounced. It's then increasing its distance away from me, so the ball is going upwards, and then it's coming back down to 0. And as it comes back down, its value gets lower and lower and lower. I am going to consider the upwards direction to be the positive direction. Notice that this arrow has a line across it, making it look like a positive sign. When we're dealing with vectors, you need to decide which direction is going to be positive. And I've decided that upwards is positive, meaning that the ball is going to stay in the positive region of this graph because it is only ever above the ground. The velocity of the graph is upwards but slowing, and then as it comes down, it is increasing its velocity towards the ground. It actually has a velocity of 0 at the top. So at the top of these peaks, I want the velocity to have a value of 0. So that would be here, and here, and here, here, and here. Velocity when the ball is coming back down is going to have a negative value. So it'll have a positive value at first, and then a negative value as its maximum negative value as it comes back down and hits the floor. It then changes its direction and starts heading upwards again. Like this. Except, as it loses energy, it's reaching a lower height each time, so the velocity isn't going to be as fast. So let's redraw that and consider the energy that's being lost. So it's going to start off at this positive and negative velocity, and that value is going to get lower each time. It's going to get less and less each time. The magnitude of the velocity is going to get lower. So let's sketch that more accurately. Okay, so hopefully you get the idea. If you do need to connect these lines together, we do it with a dotted line to indicate that this is an instantaneous change. Finally, the acceleration. Acceleration of this ball is due to gravity, and gravity will always be pulling it downwards. So we have a constant value, a negative value for gravity. That will be 9.81, negative 9.81, except for the moments when the ball reaches up, comes down, and bounces on the ground and starts going back up again. In order for the ball to go back up, it needs to bounce. It's changing its direction, it's changing its velocity. So every time it hits the ground and changes the direction in which it's traveling, it's going to need to be accelerated. And the acceleration is in the upwards direction. We had a downward velocity, and that is changed to an upward velocity during that bounce. So at the moment when it hits the ground, which is going to be here and here, here and here, at those moments we're going to have a very large positive acceleration. So let's redraw this line. I'm going to make a gap at those locations, and for an instant we're going to have a very high positive acceleration, causing it to rebound. And again, you can use that dotted line to show that it's an instantaneous change. There are 4 equations of motion that help us to calculate the behavior of objects. These equations are v equals u plus at, s equals the average velocity times t, s equals ut plus half at squared, and v squared is u squared plus 2as. We have lots of different terms here, and they are usually known as the Suvat terms and the Suvat equations. The S is for displacement. The U is the initial velocity. You may see that sometimes written as V0, or velocity at time 0. We have the final velocity. You may see that as V subscript F, F for final. We have acceleration. If the acceleration is due to gravity, then we use 9.81 meters per second squared. And finally, time, measured in seconds. So these are often known as the Suvat equations, but more accurately, they are known as the equations of motion. This first one here tells us that the final velocity is equal to the initial velocity plus any changes to velocity that can occur. So remember that velocity is the rate of change of displacement, and acceleration is the rate of change of velocity. So if we write out at by rearranging this equation, notice that that gives us the change in velocity. So this is the final velocity is equal to the initial plus any change in velocity that will occur. The next one, displacement is equal to the final plus the initial halved. So that is the average velocity. If we rearrange this equation here, displacement is equal to velocity times by time. That's what this is, the average velocity multiplied by the time. These two over here are a bit more complicated to derive. You don't need to know how to derive them, but if you're interested, you can look that up yourself.